In the previous class, we had a discussion about example of seatbelt warning system using various models. One is FSM, finite state machine. Then we have concurrent model as well as the sequential model. So in these categories of models, we have one more, it is object-oriented model. So the previous sequential comes under the category of procedure-oriented. Here it is object-oriented. So in this object-oriented model, how the model is going to describe the solution for the required design of embedded system. So the object-oriented model is an object-based model. Means here the each and individual part of the system is considered as a model. Let me go for this mobile phone itself. If you go for the old mobile phones, those are nothing but designed using keypad. So here each and individual part, it is considered as an object. So here while designing the embedded system, we concentrate on the object, okay, not on the procedure. Okay, so how we need to connect the keypad and the screen, how and keypad and the chip, microcontroller or a microprocessor, how we need to interconnect, and how what is the procedure. So we're not going for procedures here, we are going for objects, how they are going to be used. Okay, and what are the behaviors, what are the attitudes, attributes, characteristics of each and individual object. We are going to design the required embedded system. So object-oriented model is an object-based model for modeling system requirements. Means while designing system requirements, we concentrate on object. So keypad, if I go for that old mobile phone, here the keypad is one object, screen is one object, microprocessor or microcontroller is one object, panel is one object, buttons are each button is one object, volume high, volume low, power button. So these are all. Mic itself is one object, speaker itself is one object. Okay, so it disseminates complex software requirements into a simple, well-defined pieces called object. So here it is going to convert the complex software requirement into simple defined pieces. Okay, so those are segments. Those are called as objects. Object-oriented model brings the reusability, so we can reuse the object, each and individual object, maintainability and productivity in system design. So if I go for object-oriented concept, obviously the productivity of that system, obviously if keypad is damaged, means one object is damaged, and I should not think about the replacement of complete embedded system itself. Here I need to concentrate. If I concentrated on only individual object, that is nothing but keypad, yes, the developer is going to have the facility of providing these simple pieces, that is nothing but objects. So the production is also only for keypad is available. The production is only for screen is available. No need of any designing the complete embedded system itself. If it is a procedure oriented, we need to replace complete system. But what about here in the object oriented? No, we need to only replace, reuse, and maintain each object. That's it. Each object is characterized by a set of unique behavior and state. So as we know, so each object, each part, object nothing but each part. So each part is, it has its own unique behavior and the state of work. Here we are going to define those things as a class. While writing the programs, if you go for object-oriented program, we define these objects as class. So a class is an abstract description of a set of objects. So these set of objects which are having unique behavior and state, we're going to mention those set as a class. And a class represent a state of an object through member variables. So we may declare that behavior, that object behavior as a member variable and the function. So variables and functions are defined in the class. So the class member is nothing but a object. So behavior, it will be in the form of function and the object will be in the form of variable. The member variables, obviously in the object oriented programming, one of the basic example it is the C++ programming. So in the C++ programming, we are going to introduce the behavior of the introduction of classes. Here we are going to define a set of variables, functions as a class, and we are going to reuse those class variables. Whenever we want to initialize any variable, whenever we want to use that variable and the respective function, we are going to call that variable with the respective class name. So the member variables and member function of a class can be private, public, and protected. So if we go for that the C++ programming, so we are going to find these types of classes: private class, public class, and protected, and they have their own security methods. So the private member variables and functions are accessible only within the class. The private member and variables are functions. So whatever the set with respect to one class, if it is class is of type private, they are accessible within the class. Whereas the public variables and functions are accessible within the class as well as outside the class. So public, as the word indicates, it will be used by any statement, any instruction inside the class as well as outside the class. So the protected variables and functions are protected from external access. So here the public and protected. So public is nothing but anyone can use. Private nothing but within the class. What about this protected? So these are not accessed by externally. These are some introduction about how the object-oriented model can be designed. Next comes the embedded firmware design. The embedded firmware design approaches for embedded product is purely depend on the complexity of the function to be performed and the speed of operation required and other requirements. So the firmware design approaches for embedded product is purely dependent on these requirements. Those are the complexity of the function to be performed as well as the speed of operation, then the memory utilization, the input and output communication. So all these requirements will be approached by this firmware design. So in this design, we have two approaches. One is the conventional procedure based firmware design. So firmware nothing but it is a specific software written for a specific microcontroller or microprocessor or a hardware, you may say. Okay, so firmware is nothing but software, is nothing but a set of instructions, set of programs. Hardware, it is nothing but the physical part of the system. What about this firmware? Firmware, it is a software written for dedicated or a particular hardware. So it is nothing but it is combination of both hardware and software. So it is a firmware. So we need to design such firmware. Nothing but if I want to design one microcontroller and I want to write one program in that chip. Okay, if I go for the clock, so the chip hardware, which is performing only clock operation. Only clock operation. So what is the program it is written in that chip? It is stored in that chip. It is only a software which is working on clock. So you return a particular software and you dump that one in the hardware, and that hardware is in the combination of such software and hardware is known as firmware. So here there are two things. One is conventional procedure, that is super loop model we are going to call, and another one is OS, operating system based design. So based on the operating system, it is general purpose or real time. So we are going to design such firmware. I hope you got the definition of this firmware. Firmware, let me repeat, firmware, it is a software written for the unique or selected hardware. It is not written for general purpose. It is only for selected hardware. Example is the clock operation, the chip which is going to perform clock. So the software is written such that it is going to provide clock operation, and that software is written stored in a IC or a hardware. So that hardware, that IC is that combination, software and hardware, is called as firmware. So how to design? One is super loop model, another one is OS based design. So what is this super loop based approach? The super loop based firmware development approach is adopted for applications that are not time critical. Means we are writing the applications which are not real time. Time is not the requirement, where the response time is not so important. So we are not concentrating on the time here. At any time, at least it has to respond. It may take its own delays, but it has to receive the input, perform it, and produce output. The firmware execution flow for this will be how the execution steps will be. Here it is, configure the common parameters and perform initialization for variable hardware, component memory, and registers. So first the configuration is going to happen, the initialization is going to happen in the firmware execution. Then the first task will be started and executed. First is initialization of all the components. It may be memory, register, or a IO device, connectivity, whatever may be, all parameters. The common parameters are going to be configured and initialized. Then the task is going to begin and executed. First task. Similarly, second task initiated and executed. Similarly, next and next and next task. So all the tasks. Then the execution is going to come at the last defined task, and later it jump back to the first task and follow the same flow. So how the execution is going to happen in the firmware? When it is started using of that firmware, the execution begin from initialization, then task 1, task 2, task 3, and all tasks are going on executing, go on executed. Then the last task will be executed. After the completion of last task execution, the execution step, it is once again go back to first task and follow the or repeat these task executions one by one. So this is the method of used in the firmware execution for super loop based approach. So from the firmware execution sequence, it is obvious that the order in which the tasks to be executed are fixed. So whenever the task will be executed, it should have the hierarchy: task 1 first, then task 2, then task 3, and so on. Once again, the loop will be there from last task to once again first task. First task, once again, this loop is going to be go on executed in the firmware as an infinite loop. So this approach is referred as super loop because it has an infinite loop, super loop based approach. So time is not a critical thing here. So the major drawback is what? Once again, obviously, it is not a real time. One of the major things. And if any failure in any part of a single task will affect the total system. So this type of approach to design one firmware, obviously, it has a drawback that if any part in any task, if it gets failed, the entire system is going to collapse. If the program hangs up at some point while executing a task, it will remain there forever because it is an infinite loop, isn't it? It is an infinite loop. Hence, if anything at any point the system, the program is hangs up, the overall system will be hangs up forever. Hangs up for forever. So ultimately the product stop functioning. So these are major drawbacks of this super loop based approach. So another major drawback of the super loop design approach is the lack of real time concept. So real timeliness will not appear in such approach. So if the number of tasks to be executed within an application increases, if the number of tasks to be executed in the application, if they increased, instead of going for only few selected tasks, if it is a complex system and we have designed one firmware which is have many tasks, more number of tasks, obviously the time at which each task is repeated also increases. The repetition of tasks to be increases. Okay, if I go for that simple clock firmware, okay, if I go for simple clock firmware, how many tasks we are going to observe in that simple clock? If I go for the digital clock or analog clock, let me go for which is very familiar with us. It is digital clock. We can easily understand these concepts. Even we can understand that analog clock also. Let me go for the digital clock example. So here, there, the digital clock firmware, okay, means a software written and it is stored in a chip, and that chip is going to be used for what? Displaying the digital clock. So here in that one, how many tasks will be executed? And they will be in the infinite loop, obviously. Until unless the battery power it is going to be slowed down, the process is gone running in infinite loops. Task 1, then task 2, then task 3. Once again, go back to task 1, task 2, task 3. Once I made that system on, digital clock example device on, first what it is going to do, it is going to configure all the things, first step, then initialize all the components, then begin with task 1, task 2, task 3. So in the digital clock, here I am going to observe only 3 tasks as an example. Okay, it is purely one example. So the task number 1 is what? I need to start and complete it. What is that one? The second digital values. The values which are related to second parameter. Seconds from 01 to 59 variations. Then after completion of task 1, I need to move towards what? Minute. The variables which are dedicated for minute parameter in that digital clock. So second task will be executed. So based on that one, the input is read, performed and executed. Then what about after minute? The third task is the display of hour parameter. So the hour parameter, it is once again the third task will be executed. After the completion of that third hour, that is third parameter, that is our parameter in the digital clock, what is going to happen? Once again, we kept that execution in a loop. Means what? Once again, the second parameter will be executed. After second parameter, the minute parameter. After minute parameter, the hour parameter, and this thing will be in the loop. So in this system, if the one part is hangs up, suppose the minute is not increasing, minute parameter is not performing its task, it is struck at that time. So what about the entire system? Obviously, the entire system is going to stop its functioning. So this is the drawback what we are going to observe in super loop based approach. And obviously, the number of tasks are increased. Obviously, if I go for hour parameter, it has to wait for what? Minute parameter task, as well as the minute parameter is already waiting for second parameter. Now, if I increase it once again, what is going to happen? The nth task, obviously, a time consuming work. It is a time consuming work. So because of some increased applications, obviously we are going to find it brings the probability of missing out some events. Okay, so this is about super loop based approach. Next, we go for designing that firmware using embedded operating system based approach. So OS based. So how it will be? So the OS based approach, it contains the operating system, which can be either, as I said, it is a general purpose operating system or a real-time operating system. So real-time operating system, you are going to learn more about this operating system in the next module, module number 5. Okay, to host the user written application firmware. So here the OS is going to be used for hosting the user written application firmware. And here the example of the GPOS used in the embedded product development is the Windows XP, what we are familiar with, the general purpose operating system. Means whatever the firmware we return, we are going to use this platform, the OS platform, for execution. The real-time RTOS, real-time operating system based design approach is employed in embedded products demanding real-time response. Where there is a demand of real-time response, we are going to keep that, host this firmware in that RTOS environment. The RTOS respond in a timely and predictable manner to each event. Because the RTOS allows flexible scheduling. Obviously, you are going to have more discussion about these concepts in the next module. Okay, it is once again, let me have an introduction of this RTOS in module number 4. It is going to allow the flexible scheduling of system resources. In the scheduling also, they have so many concepts. The resources like CPU, when it has to perform, there is a schedule for CPU operations, for memory also. For means each object, each part, it is scheduled. CPU is scheduled, memory is scheduled, and the communication between the task also it is scheduled. Obviously, if I go for the execution of that assembly level code, obviously it is a scheduled one. After completion of first statement, next statement has to wait. Okay, what is the time when it is scheduled? The second instruction, it is the second instruction is scheduled after the completion of first instruction, like that. Okay, and we may go for interrupts. So interrupts are also scheduled, or the program execution is also scheduled. This is nothing but what? Everything is CPU. CPU operations, memory operations, and all communication tasks will be scheduled with flexibility. Example of this RTOS are Windows CE, PSOS, VxWorks, ThreadX, Micro C, embedded Linux, and the most using operating system in the mobile phone, Symbian. In the mobile phone, the most operating system it is Symbian, real-time operating system. Our example of this design of embedded firmware based on OS approach. Next comes, yes, we got the idea about how the firmware, a specific hardware is designed using a dedicated software for it, a firmware, how it is designed. Then we go for what is the language we need to prefer during the development of that firmware. So the title is Embedded Firmware Development Languages. So which language we need to prefer to design such firmware? The example is the digital clock itself. So I want to design that chip. I want to write a program and I want to dump in a chip, and that chip is performing what? The digital clock display. So which language I need to prefer to write up software? Obviously, we are well known about these languages. Here, these are divided into three things. One is assembly, high level, and mixed. Assembly, high level, and mixed. So here, obviously, you are well known about assembly and well known about high level. So it is a new thing for you. It is mixed, means we can mix both. I can write a program, a C program is written with the microcontroller programming, that is assembly level codes, instructions. Okay, so how it is? Let us begin with the assembly language based development. So in the assembly language based development, once again it is an introduction about assembly language. In this part, we are just discussing the introduction, how it is the development environment. So assembly language programming is a task of writing processor specific machine code in mnemonic form, converting the mnemonic into actual processor instructions, that is machine language, and associated data using an assembler. So here the assembly language is going to use the mnemonic forms, and we need to convert these assembly language programs into the machine level language instructions. So for that thing, we are going to use assembler for converter. A general format of an assembly language instruction is, obviously we are familiar with, it has a first field, it is opcode, followed by operands. So opcode may have or may not have operands. So we have instructions based on various platforms, various microcontroller and microprocessor. We have the assembly language we have, which has with and without operands, the opcode we may use. So the opcode tells the processor what is the opcode. So opcode tells the processor or controller what to do. Operation code we are going to call. Opcode nothing but operational code, what the system has to perform. Then what is the operand? The data or the information is provided by the operands. It is not necessary that all opcode should have operands. We are familiar with this one. The operand may be a single, dual, or more, based on the type of processor or controller we are using. Then assembly language instructions are written one per line. We are not going to write a cascaded fashion of these assembly language instructions. Per line, only one instruction we are going to write using the format opcode followed by operands. Operand may be 1, operand may not be there, operand may be 0, or maybe only one operand, or 2 operands, or more, based on the type of processor or a controller we are using. Example is we are familiar with it is MOV opcode, move instruction. Move instruction. MOV is the opcode and it is going to use two variables, two operands. One is A, let me say it is a accumulator A or a variable or register label or anything. It may be anything. As an example, operand 1 is A, operand 2 is number 30. So this instruction mnemonic moves decimal value 30 to the 8051 accumulator register. So this example, what it is shown, it is purely for a 8051 microcontroller, where A represent the accumulator register and hash 30 represent a number, which is going to be stored in accumulator through instruction MOV, move A comma hash 30. Move the decimal value 30 to the 8051 accumulator register. So we are quite familiar with these assembly language. So this is about nothing but by using such languages we can develop the embedded firmware. So if we talk about some more things about assembly level language programming, so it has two fields, but actually it has the two parameters are basic requirements are opcode and operand. So some more two fields are labeled as label, then comes opcode, then comes operand, then comes comment. So here the label is an optional field. So as I said, it is optional. It may be there, may not be there. So it is an identifier used for remembering where data or code is located. So this label is going to tell the address of the instruction. Address of the instruction in the code memory. In the code memory where this instruction is available. It is known by the label field. So it represents memory location, address of the program, subroutine or code portion, whatever it may be used. So whenever we are writing the loops, while writing the loops, obviously we are going to use this label, go to semicolon, go to colon, like that. Okay. Next one, loop 1, loop 2. Obviously you went through these assembly language programming from the previous lab experiments. You come to know, yes, the opcode is it is written after the label statement. The opcode tells the processor what to do. The operand provides the data and information to the processor while doing the task. Then comments are not executable statements which are used for mentioning hints. So this comment is going, it is the field which is not executable one, and it is just going to tell what this statement is, what this instruction is. It is a hint. So the assembly language program written in assembly code is saved as the file name .asm. Whenever in the previous lab example experiment, when you are dealing with assembly language programs, obviously you are going to save that file as a .asm extension. So sometimes some of the programming environment are going to use, softwares are going to store those assembly languages as .src source. .src as a source. Okay, as a source or as a assembly file. So any text editor like a Notepad or a WordPad from Microsoft, or the text editor provided by any integrated development tool. We are going to call that tool as a IDE tool, integrated development tool, can be used for writing the assembly instructions. MASM example is MASM, MASM. We can write the MASMs, we can use that MASM IDE tool for writing these assembly programs. And we can open those programs, those are nothing but .asm file as well as src file using any one of the tool, that is Notepad or a WordPad or a text editor. We can use any platform. The translation of assembly code to machine code is performed by assembler. So we're going to discuss these things in the next concept. The assembler, how it is going to convert, how it is going to translate assembly code into machine code. The conversion of the assembly language to machine language is carried out by a sequence of operations. So as I said, we are going to discuss now what is the assembler performance. So here, the set of sequences are given in this diagram. So here, there's a source file, that is .asm file, our program, which is written in the assembly level code, which will be converted into, which is going to be converted into another file structure, that is the object file. It is going to be converted into object file using a module assembler. Through this object file, we are going to once again convert those things into library files. Convert object file into library files, .lib, object file, .obj file, then library file, .lib. Those things are going to be linked to this conversion assembler through linker and locator. Then what is going to happen after the link and locator? They are going to generate another file, which is nothing but hex file. It is .hex. I think you used this one in the previous experiment, lab experiments, while storing your program into chip. While storing the program into chip, you need to convert those assembly or high-level language into hex files. .hex. Hex file, we are going to say nothing but the machine code. And it is going to be, this is the method, how to convert the source file, that is assembly.asm into .hex. Okay. So if I go for discussion about these things, it will be the source file to object file translation, then library file creation and usage, then linker and locator, then we are going to perform object to hex file conversion. So these are the 4 steps, sequences used to convert assembly language into machine language. So what is this source file to object file translation? So each source, as I said in the diagram, each source module is written in the assembly and is stored as .src or .asm file. So on successful assembling, means after compiling that program, removing all errors, debugging the errors, the program is with 0 errors, 0 warning. Then we are going to what? We are going to execute that one. We need to convert that one into machine code. So that is nothing but what? On successful assembling, we are going to call that compiling in the high level language, assembling in the assembly level language. So assembling nothing but debugging the errors of each file. Corresponding object file is created with the extension .obj. So the conversion of .asm to .obj is going to happen in the step source file to object file translation. Then the next performance is library file creation and usage. So library file creation and usage is nothing but what? Libraries are specially formatted, ordered program collections of object modules that may be used by a linker. So linker is going to use these .obj and .lib files. So library files are what? These are collection of the program object modules. It is collection of object modules. Okay. So here we are going to use these library file in some kind of source code hiding technique. It is some kind of source code hiding technique. Then after library file creation and usage, means here we are going to have specific code for each object model. Then we are going to use this linker and locator performance. This linker generates an absolute object module by extracting the object modules from the library. It is the responsibility of the linker to link any external dependent variable or functions declared on various modules and resolve the external dependencies. Means what? This linker and locator, what the performance it is going to do. In the assembly level language, you have written, you have used some modules without writing the code for them. You just simply using those modules. Let me say the function you written in one file, and you are going to call that function in the another file. So how the things will be related, how the collection will be done, how the linking is going to happen. End of the day, end of the program execution, it is only single file, hex file, it will be converted. But what you have written, you written one procedure in one file and you are calling that procedure in another file. Means what? There is a linking has to happen. The linking between one file to another file. Not only linking, the locator, nothing but what? It is going to locate where, what is the address, where it is located. And it will be made one single program. Okay, so that task will be, means it is going to create one object module. Okay, extracting from library file, extracting from object file. It is going to create its own absolute object file. Absolute object file. That is the task done by this linker and look. Then the last task is what? Convert that absolute object file into the hex file. So that is known as object to hex file converter. So this is the final stage in the conversion of assembly language to machine language. The name of that file which is converted, it is has the extension .hex, H-E-X, what we're observing here. .hex is a representation of machine code. So in your computer, if you observe .hex file somewhere in the hard disk, obviously that file is nothing but it is a machine code which is generated from any assembly level programming or high level programming. Okay, so this one is the topic we covered in this session. So in the next class, we deal with the high level based development.